Okay, the possible values of n are 1, 2, 3, etc. Just keep going up. Okay, starts at 1, goes up by integers. So when we talk about that, here is a diagram of an s orbital, and we'll need to get to we'll get to L, which is our angular momentum quantum number. But this is an s orbital, okay? If you have a 1, a principal quantum number of 1, all the s orbitals are, this is a 1s, this is a 2s, kind of showing the 1s inside the 2s, but of course the size gets bigger, okay? So the 1s, this is if you were to look at where you find the electron or where you're likely to find the electron. Here it says probability of finding electron. Remember, electrons are sort of like a cloud. What they are really is a standing wave. They're kind of everywhere at once until you somehow measure them, and then they coalesce to being at a spot. Weird stuff with quantum mechanics. But 1s is pretty close to the nucleus. 2s has some stuff close to the nucleus. It has a region, we call this a node, where there's nothing, and then it's farther out. So it's bigger. Mostly you can think about that. They get bigger as the quantum number, the principal quantum number goes up. Does that make sense, kind of what we're talking about? This is visually what it would look like if you were to be able to see it with your eye. Note that there's no chance, well, the probability is very, 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 very low. I'm sure there is a chance because it's quantum, but it's very, very low that it is actually at the nucleus. Why might that be? Why is it super low chance that you'd have an electron at the nucleus? Can't have two things in the same place at the same time. Okay, that's the Pauli exclusion principle, actually. We'll use it for electrons later. But the quantum numbers also correspond. The quantum numbers also correspond to the row on the periodic table. This is quantum number 1. This is quantum number 2. This is principal quantum number 3. This is 4. These are 3s. We'll talk about, look at all our 3s. We'll talk about how it gets complicated. Questions? Okay. Our next quantum number is L, angular momentum quantum number. Okay? Possible values. So this is the shape of the orbital. It's going to tell us about shape, and you could think about it as energy sublevel. All right. When I say it's the shape of the orbital, it's often a collection of orbitals, not for the S. And let's talk about what the possible numbers are. So possible values. Possible values are going to be 0, 1, 2, 3, ... out to n minus 1. All right, so this is telling you when we say n, we're using n, right? That's our principal quantum number. It's telling us when we go back to our principal quantum number, it limits how many of these sublevels we can have. Okay. I'm going to give you a little table here because we're going to talk about these things as S, P, Ds, and Fs instead. So L, if L is this, we call it an S. I'm just going to say letter designation. Okay, it's a letter that we give to it. 1 is going to be a P, 2 is going to be a D, 3 is going to be an F, and we don't need to go to G because we've run out of elements. Okay, we need more elements to be able to do that. But what that means is if n equals 1, I'm sorry, if n equals, 1, L values could be what? if they can go all the way up to n minus 1. N is 1. Yeah. 0. All I can have is 0, right? Okay. If n is 2, I can have 0 or 1. If n is 3, I can have 0, 1, or 2. Does that make sense? And so what that gives us is we could think of a nifty little diagram, which isn't in your book, but I was taught. I had to look up to remember exactly how it worked. I'm not going to make it work just yet, but you can go. So when you think about that first level on the periodic table, it has one S, and that's it, right? Because all we can have is 1, we can have 0. It's going to have 2S and 2. Then it will be down to the next level, 2S and 2P. Okay? And then we have 3S and 3P and 3D. And 4S and 4P, 4D, 4D, 4F. Okay? We're not going to worry about these F's as much. Might worry about them a little bit, but I mostly want to focus up here so we get the concepts. But so, 1S, 2S, 2P, 3S, 3P. Here's our D. It gets a little complicated here, 3D. I'll show you a cheat thing or a little phenomenon or whatever that'll help you remember that. But 3D is here. That's our 4S. That's our 4P. Okay? When we talk about these sub-energy levels, which are a collection of these orbitals. Questions on that? Okay. Yes?
Where's the F at?
The F's, that's a great question. The F's are down here, right? We write them down here. They fit in. This is actually a great periodic table because it's just really old, but it's a great periodic because it doesn't tell you where they fit in over here. And depending on which periodic table you pull, whoever the author was will fit them in different places. But they're going to insert in when we think about putting our electrons in. We're not going to do a lot with worrying about exactly where they insert in beyond whether they insert very specifically where they insert in. We may do some things with F's. We're just going to assume they insert in at the beginning of the right after the S. And I'll show you how we do that in a minute when we start filling in energy levels. So this is an example right here. This is a p orbital. Okay, so it has quantum number. Oh, and let's go back up here. So possible values, actually, it has quantum number 1, right? Okay. So a p sublevel, which is a sub-energy level you could think about, is, these are each p orbitals when I talk about an orbital. It's a combination of 3 p orbitals. One that looks like this, one that's in this, and one that looks like that. They're all kind of barbell sort of shaped, dumbbell sort of shaped. But they're at different directions, whether they're on the z-axis, the x-axis, or the y-axis. Okay? Different than the S. The S was just a sphere. Okay? I'll have pictures of all of these later. Oh, no, maybe I'll have pictures of them right now. Here is a D sublevel. Okay? So D. Now instead of 2, so the D sublevel is all these together, which I guess they didn't give us a picture because it's just confusing. It's just a bunch of stuff overlapping. But remember, this is L equals 2, okay, for this sublevel. This is L equals 1 for this sublevel. This up here is L equals 0 for that sublevel. Okay. All right, and I did do F's. Here are what the F's look like. Do you see how each time we're adding more? We're adding more stuff each time. So here we had, for each orbital, we had 2 lobes, right? When we look over on the left there, here for each orbital, and each orbital here, each of these orbitals will hold 2 electrons. We'll get to that. Here, we have 4 lobes mostly. We have this funny looking one with like the little Saturn ring around it. What these represent is these are where you'll find the electrons. Remember that. That's what these orbitals are about. Where are the electrons? So for a d sublevel, I can put 2 electrons in this, 2 in this, 2 in this, 2 in this, 2 in this. How many electrons can I put in a d sublevel? Actually written that, but 10, right? 2 in each I can put in. I don't have to. All right, and then we can have L equals 3. And that is our F sublevels. And so you see they've added more of these again. So for these, it's obvious. Now we have 8, right? Looks like that is only 6. Looks like some of them are only 6. And what these numbers, I'm giving you these numbers for this, but what these numbers do is they go into equations that when you do the calculation, it tells you where the electrons will be found. Okay, you put N in, you put L in, and these things pop out, okay? And people smarter than all of us have figured this out, okay? Super high level math. Maybe they're not smarter, but they're lots better at math than probably all of us. Okay, questions? All right, so that's L. So I've already sort of talked about, I'm going to define it here, and then we're going to have to go back to our pictures again. So we then have M sub L, which is our magnetic quantum number. Okay, and that tells us the orientation of the orbital. And now we're talking about orbitals, not sublevels. Okay, so, and the possible values. Are going to be minus L to plus L. Okay? So if L equals 1, then M sub L is equal to -1, 0, and plus 1. Those are my possible values. That makes sense for that example? So let's go up to our orbitals again. So we just did this one. So M sub L here is going to be equal to, that's not a sub L, M sub L here is going to be equal to -1, 0, 1. And I'm sure that these are designated which is which, but one of these is -1, one of these is 0, and one of these is +1 in terms of the orientation. Does that make sense? I'm going to go ahead and I'm just going to circle okay, and point to those and pretend that I've got that right, and I may not. It doesn't matter. If you go on to be a physical chemist or a physicist doing this, you will fix that in graduate school. You'll know which is which. Okay, let's do this then. What are my possible values here for M sub L for this set of orbitals?
Is it -2, -1, 0, 2?
Absolutely. Very good. Okay, those are my values. How many values do I have? 5. How many orbitals do I have? 5. Each takes 2 electrons. That makes sense? So that's how this sort of stuff pops out, how many orbitals we have, which is going to be important to us in terms of explaining how the electrons surround the atom. We're not going to do this one. I think you guys have it. All right, final quantum number is our M sub S. That's our spin quantum number. I've been saying you can put 2 electrons in each orbital. Okay, but they're filling the same space, right? And they're kind of everywhere. Well, they have different spins. Their spin can be -1/2 or +1/2, and this is what tells us that we can put 2 electrons in each orbital. Okay, so 2 electrons per orbital. And what this is doing is it fixes 2 things in the same space at the same time. Questions? All right, so then now we have what we need to know to build an energy level diagram. So this is what we call an energy level diagram. Let's call it electron energy level diagram. Okay, it's an energy level diagram in general. And so what we can do is if we're putting electrons into this diagram, this is the diagram that we'll use for all atoms. And we would essentially we'll figure out how many electrons we have for an atom and we fill them in. Okay, that makes sense. Makes sense? So we go ahead and we fill these things in, and we fill them in from lowest energy to highest energy. So what we can say is electrons will occupy the lowest energy possible. They'll occupy the lowest energy orbital possible. All right, and we'll see this in chemistry again and again. Things like to go from high energy to low energy, or they like to just be at the lowest energy. So let's say we're going to do, so we could do an electron energy diagram for, let's do one for neon. How many electrons does neon have if it's neutral, which it almost always is? How many protons does it have? You over here, hopefully you have your periodic table still. Yeah, Damari. 10, right? It has 10 protons. If it's neutral, it has 10 electrons, right? So we're going to say 10 electrons when neutral, uncharged. So we need to put 10 electrons into this diagram. So I'm going to put 1, 2, and what I do is I do an up arrow for one of the spins and a down arrow for the other spin. You call the up arrow the positive and the down arrow the negative. It doesn't matter for the quantum number, right? But I can put 2 in. I'm doing up and down to indicate different spins. So 1, 2, 3, 4. Next level up is this 2p. So we'll put those in. 3, 4. Now, when you try to put 2 electrons into the same orbital, they've got different spins, but they're still sort of in the same place at the same time, so they don't like to occupy the same orbital. All right, so you don't do that unless you have to. All right, so the way I would fill this, they're all going to end up paired for neon. But the way I would fill it, I'd use 1, 2, 3, 4. I would fill it like this. I'd go 1, 3, 4, 5, 6, 7. I'd split them up so they're in different orbitals, and then I have to fill the orbitals now. 7, 8, 9, 10. So for his, this didn't matter, but it will matter for other ones. Right? And that's the electronic configuration of neon. or it's the electronic energy diagram, but it's the configuration as well. We'll have something specifically called electronic configuration diagram here. Okay, let's make our own, but I want to show you something here. We're going to make our own next because you're going to have to make your own on the test. Notice that we go, so we do all the ones, then we do all the twos, then we do all the part of the threes, but then this 4s is lower energy than the 3d, right? You see that? So we're going to fill this one before that one. It's kind of confusing, okay? And so they end up out of order. So you're going to have to know what the orders are, but I'm going to give you a trick that makes it easy. Otherwise, I wouldn't make you know what the orders are. All right, so this is what they taught me when I went to college. You essentially write your orbitals. Remember I wrote this out earlier? I'm going to go out to 5 in case I need it. I'm not going to write a G because we'll never use it. All right, so now what you do when you want to figure out what order do these things go in terms of energy is you're going to draw diagonal lines. 1s comes first, then 2s, then 2p, then 3s, then 3p, then 4s. So see, that's telling you that the 4s comes before the 3d. Then 3d, 4p, 5s, all right, etc., all the way down your diagram. That's how you know what order they come in. All right, so let's go ahead and let's do something that's going to cause that to happen. Let's do arsenic. Arsenic is number 33 on the periodic table. If you can't see the periodic table over there, then please use the one you've got. Okay. Arsenic. How many, let's say arsenic is neutral. How many electrons is arsenic going to have if it's neutral? 33 electrons. And let's go ahead and draw our diagram. So our diagram is going to have 1s at the bottom. It's going to next have 2s, right? I'm following my diagram here. So write 1s, 2s, 2p, 3s. Two p has how many orbitals in it? 3. P's have 3 in them. Quantum number, or L, angular momentum number 1, -1, 0, +1. You don't have to do that, but you just remember that there are 3 orbitals for P's, okay? I'm naming the quantum numbers for you for it, but I just remember it has 3. 2p, right? So 2p, then 3s. Then 3p, then 4s. Okay, then 3d, how many orbitals in the d? 5. So it's going to be 1, then 3, then 5, then 7, right? Easy pattern to remember for S, P, D, F. All right, 3D, we're here at 3D on my diagram. Now 4P, now 5S. And then 5S. All right, hopefully that'll be enough to get me through arsenic, right? So now I'm going to count to 13. If you've been following along, let me give you 30 seconds, or let me give you a minute here. You've been writing those orbitals, hopefully. Go ahead and fill it in. And remember when you're filling in those P's, or when you get to the top, that you need to fill out individual at 1 electron per orbital first, and then you add more, then you pair them up. All right, I'm gonna fill them in, make them red because it stands out really well, but I've got to put 33 in. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33. Boom. That's what we got. I filled them from the bottom to the top. I made my orbital diagram using this tool. Okay? And that's what the electronic energy diagram for arsenic would look like. Any questions? Okay. All right, you can imagine this will get tedious, right? When we draw this. These things are useful, but what we do is we have a shorthand, which is called an electron configuration diagram. All right, my electron configuration diagram would look like my energy diagram, except I can write it all in one line. It doesn't take half a page of paper. All right, so I'm going to do the same thing for arsenic here. And then I'm going to show you another shortcut that's going to make them even faster to draw. All right, so what I can do is I can write these out and go 1s, right? And that has how many electrons in it? The 1s. 2. 1s2 with a little superscript 2. 2s has 2. 2p has 6. 3s, 2. 3p, 6. 4s, 2. 3d is going to be 10. I can count. And then 4p is going to be 3. This is an electron configuration diagram instead of an electron energy diagram for, and I'll be specific, but electron configuration diagram for arsenic. Questions on how that works? Okay. Let's look at this with the periodic table. So I don't even do these by counting up all the electrons and filling them in like that. I do it using the periodic table. So I go, okay, my first row, 1s, right? I'm here at arsenic. There's arsenic right there. First row, 1s is full. 2s is full, right? 2p is full. 3s is full. 3p is full. Okay? I need to remember that these lag by 1. 4s is full. 3d is full. Now there's arsenic. All right? 4, we're in the fourth row. 4p, 1, 2, 3, I'm done. Okay? Does that make sense? How that would work? All right. Let's talk about the octet rule. And we're going to go back to this. 8 electrons in the outer shell is especially stable. Okay? My other way of saying it is everybody wants to be a noble gas. So what that means is when I say 8 electrons, I mean even though we might have, so if we have this, right? what is the outer shell here? What's the principal quantum number that's the highest on this row? Principal quantum number, what's this principal quantum number for this row? 1, 2, 3, 4. Principal quantum number for this row that's highest is 4. Full outer shell would be 2 in the 4p and 6, 2 in the 4s and 6 in the 4p. Right here, and then this is the lower shell. Even though it's higher energy. Good fill. Okay? And the noble, so what that means is that's to fill all those up, we have to be krypton over here. Okay? These are our noble gases. They have full outer shells. So they have, the 2p is full, the whatever p is full, and there's 2 electrons in the s, 6 in the p. They have full outer shells, and they're really not very reactive. They don't really interact. They call them noble, they're snooty. They don't want to interact with anybody else. It's because they have plenty of electrons and they're happy. Okay, they don't need to share electrons to fix things. And we'll find out later that sharing electrons is how atoms will get sort of 8 electrons in their outer shell. Okay. Questions so far on that concept? All right. So, say noble gases are very stable. They're very stable and don't react with anyone. React with, let's say, other atoms. Okay. Let's also talk about ions. This octet rule is going to be related to how we think about ions. They are charged particles in general. Okay. In our case right here, we're going to talk about charged atoms. So we're really going to be talking about charged atoms and molecules. All right. So it turns out we have certain atoms will take on certain charges, all right, based on the row based on the column in the periodic table they're in. And that's following this octet rule. They're trying to be noble gases. All right, so they're going to take up certain charges to fill up their outer shells to be like noble gases. So let's go ahead and think about, now we're going to go back to other thing. What would be the stable form of fluorine? Fluorine's number 9, right? So what ion or what charge will fluorine have to become stable? And what we're going to do is we're going to use our electron configuration diagram to figure that out. Draw an electronic configuration diagram for fluorine. Okay, so that's going to be our 1s, 2s, etc. And you're going to put how many electrons are in each of those. Go ahead and do that. Take a minute and draw it for fluorine. It has 9 electrons. We're going to do it for neutral fluorine, which honestly doesn't really exist. I suppose you could make fluorine gas F2. I'm not seeing much of it. You should probably run. You got fluorine gas around. Okay, so let's go, let me go ahead and finish that. So I'm going to need 2p next, right? I'm going to use my diagram to figure out which ways these go. Then I'm going to need 3s. I'm going to use my diagram, or I could just look at the periodic table, right? I just wrote 3s. Do I need to write 3s? I don't, because fluorine's in the second row. I never even get to 3s, unless I'm going to need to write it somehow to make my ion. But we're not doing our ion yet. All right, so 9 electrons, right? 2, 4, and I need 5 more. Is the P full? Okay. How could I easiest, so the ways I could make my outer shell full, right, is I could add 1 electron, right? Or I could take away 7. Which is easier, do you think? Adding 1 or taking away 7? Adding 1. Okay. So what I can do is, this is neutral fluorine. But if I went and I just added 1, let's call it ion fluorine, okay? Add 1 electron to get a full shell. And so if I add an electron, what ends up being the charge for fluorine? What is the charge on an electron? Negative, right? And so if I add that, so the ion fluorine is going to be fluorine minus. Okay, and you'll often see me circle these charges. You can do it or not. Questions? So fluorine, and everything in this row, you see that, remember our noble gases have our full shells, right?